You ever grab your fancy digital calipers with their shiny metal grip and discover that they won't work? Maybe the battery died. Maybe there's no battery at all. But now you have to hunt around to find one, and if that fails, you're now driving to a hardware store to buy some, or ordering them off of Amazon. Well, I know I have, and I hate it. After this happened to me a few times, I gave up and bought mechanical calipers. But are they precise enough? I mean, the shiny metal grip digital calipers were so precise, they could read down to 0.005 of an inch. These mechanical calipers only have divisions down to 25 thou. That's where the Vernier scale comes in. In this video, I'll show you how to read a Vernier scale so you can get very precise measurements off mechanical calipers. These go all the way down to 1 thou of precision. I'll also explain the principle behind why it works, including some stuff you won't find in other tutorials. So let's say you want to measure something very precisely. You've placed it in your calipers, firmly held the jaws closed, and locked down the slide. Now you can inspect the scale up close. The 0 line on the vernier reads 0.1 inches plus 0.025 inches. That's your basic low precision measurement, so we'll write those down. To get the precise measurement, we first check if the 0 of the Vernier scale is aligned with any increments. If it is, we'd stop. Since it doesn't, we look for the mark on the Vernier scale that best aligns with any mark on the main scale. This one is pretty far off from a main scale mark. This one looks very close, so this is the one I'll use. The units of this Vernier scale are in thousandths, so we count off how many increments over this mark is. Looks like 8 thou. We add that to our measurement, and add them up to get the final precise measurement of 0.133 inches, plus or minus a thou. Let's take a look at why this works. Here I've made a model of the scales on Vernier calipers. There are 10 increments on the main scale. On the Vernier scale, you can see that there are also 10 increments, but that the scale is slightly shorter by 1 increment of the main scale. Therefore, the length of the increments on the Vernier scale is 1/10 short of the length of the increments on the main scale, or 0.9 units long. If we want to align the one on the Vernier scale with the one on the main scale, it must move up by 1/10 of a main scale increment, 0.1 units. Now the distance between the two zeros is 0.1 units. Sliding the Vernier scale further, to align the twos, we must again move 1/10 of a main scale increment, or 0.1 units. The distance between the zeros has increased to 0.2 units. Aligning the fives, we move the Vernier scale by 5/10, or 0.5 units, and the zeros are now separated by 0.5 units. Aligning the tens, we move the Vernier scale by 10/10, or 1 unit, and the zeros are now separated by 1 whole unit. If the Vernier scale is short by 1/10 the total length, but the number of divisions is reduced to 5, each increment of the Vernier scale is shorter than the main scale increment by 1/5, or 0.2 units. The Vernier principle still applies, just with a doubling factor. Aligning 1 with its double 2 produces the same result, and the Vernier scale has moved 0.2 main scale increments. The precision of the Vernier scale is determined by the length of the Vernier scale, and by how far short it is of the main scale. Here is a Vernier scale that is 1 main scale increment short of 5 main scale units. As each corresponding increment aligns, the Vernier scale has to move by 1/5 of the short amount, or 0.2 units. Therefore, this shorter Vernier scale has the same precision as the longer Vernier scale, with 5 divisions, because the length of the difference is still 1 main scale increment, and the Vernier scale has 5 increments. The relation is captured by this equation. The precision of a Vernier scale is equal to how far short the scale is, divided by the number of Vernier increments. To get more precision, we simply need a longer Vernier scale. One that's 1 short of 20 main scale increments, with 20 Vernier increments, has a precision of 1/20th of a main scale increment, or 0.05. On the mechanical calipers we saw before, the largest numbered units are inches. The next largest unit that's indicated is the 1/10 of an inch, with only the even subdivisions numbered. The smallest unit is 1/40th of an inch, or 0.025 inches. This is the main scale increment. The Vernier scale is one main scale increment short of 1.250 inches, or 50 main scale increments. It's divided into 25 increments, and by our equation, the precision is therefore 1/25th of 0.025 inches, or 1,000th of an inch. An inappropriate choice of short length will ruin a Vernier scale. Consider this one, which is too short, of 10 main scale increments, with 10 Vernier scale increments. This is a ratio of 8 main scale increments to 10 Vernier scale increments. However, the 4 and the 5 line up just as well as 8 and 10 do. 8 and 10 share a common factor of 2, and so the ratio 8 to 10 is the same as the ratio 4 to 5. When we move the 1s into alignment, 5 and 6 are also perfectly aligned. When the 2s are aligned, so too are the 6 and 7. We can see that there are 2 Vernier increments that align well with main scale increments instead of just 1, leading to an ambiguity. In principle, this isn't a problem because the lower of the 2 is always the correct one. However, real calipers typically have so many markings that the duplicated alignments become confusing. This is only compounded by inaccuracies of the markings and the effects of parallax, which can make determining the best alignment rather difficult at times. For this reason, Verniers typically only use ratios where their terms have no common factors. The easiest way to achieve this is by simply picking terms that differ by only 1,